Here is a mechanism problem. Let's imagine that we begin with the following alcohol. Here it is. And then this is a spirofused compound. So there's a 6-membered ring here, and then there's a 5-membered ring there. And then this compound was treated with acid. So in this particular case, it was phosphoric acid. This was heated up a bit, and the final product looks like this. Has a double bond right there. So this type of problem is a so-called mechanism problem. So your job is to give the mechanism. Recall that in mechanism problems, you're given the starting material, you're given all the reagents and conditions, and you're given the product. So you're not allowed to bring in some extraneous reagents or different starting materials or any manipulation of that kind. Your job is to propose a reasonable set of chemical steps to get us from here to here and to illustrate those steps using the arrow formalism. All right? So I'll just give you a chance to go ahead, and if you think you know what to do, pause the video and go ahead and do it. And if you get stuck, or if you have no idea how to begin, perhaps you can continue, and we'll try to do it in a series of steps, pausing from time to time to give you a chance to work things through on your own. In a mechanism problem, a good approach is to try to look for the differences between the starting compound and the ending compound. One way is in terms of molecular composition. So for instance, can you figure out what the molecular formula of this starting material is, and then compare it to the molecular formula of the product? So maybe pause the video and do that. The starting compound has 6, 7, 8, 9, 10 carbons. So this is C10. It has 2, 4, 6, 8, 9, 10, 12, 14, 16, 18 hydrogens and 1 oxygen. And then on this side, we also have 10 carbons. We have 2, 4, 6, 8, 10, 12, 14, 16 hydrogens, and there is no oxygen in the product. So if I compare this formula to this formula over here, what's the difference? The difference are 2 hydrogens and 1 oxygen, which maybe stimulates us to think about loss of H2O. So in terms of getting started, somewhere along the line, we're going to have to lose the elements of water. Another very good approach in mechanism problems is to try to find the correspondence, or guess at the correspondence, between the atoms in the starting compound and the atoms in the product. And one way to look at it is look at the type of carbon. Is the type of carbon a CH2 carbon? Is it something other than a CH2 carbon? So see if you can't somehow label, maybe by numbering, the atoms on this side. So we're all on the same numbering scheme. Maybe let me just number the atoms over here in some perhaps sensible way. There they are, the 10 carbons. Make a guess as to where those carbons end up on the product side. Well, maybe given that this carbon 2 right here is a CH2 carbon, and there's 1, 2, 3, 4 CH2 carbons in a row, 2, 3, 4, 5, okay? And then maybe this one is 6. And then carbon 7 is a CH2, 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 like that. So perhaps it's like this, 8, 9, and 10, like that, okay? So that's a guess. I may be wrong. I may have to be reevaluating this as I go along, but maybe that's a good first place to start, okay? And then this carbon then would be carbon 1. So again, in mechanism problems, it's not a bad idea to think about what has to happen during the course of this reaction. So if you look for bonds that are present over here but are absent over there, those are the bonds that we need to break. So we can even make a little list here. So we need to break the bond between 1 and oxygen. So notice there's no OH group attached to carbon 1 over there. There's also a hydrogen at carbon 1 in the starting compound, and there isn't one there in the product. So we have to break that bond as well. In the starting material, carbon 10 is connected to carbon 6, but in the product, it is not. So I need to break the bond between carbon 10 and carbon 6. And then there are some bonds that I need to make. So in the product, 10 is connected to 1, whereas over here it isn't. So I need to make a bond between C10 and C1. I need to make a double bond between carbon 1 and carbon 6. So I need to make a pi bond between carbon 1 and carbon 6. Carbon 1 and carbon 6 are already sigma bonded in the starting material, but in the product there's a double bond there. And maybe that is it as far as what I have to do. So sometimes this kind of analysis will give you a checklist so that as you go through your mechanism, you can see whether you're accomplishing anything on this list. If you start pushing arrows and you find this list is not getting any shorter, then maybe you started in the, on some incorrect pathway. Okay, so having this to-do list is sometimes useful. Well, at some point, you've done as much analysis as you need to do or want to do, and you have to get started. So then you start to think about, all right, do these conditions look at all familiar, involving loss of water? And you may be prompted to think about a particular type of reaction. So if you look at these reaction conditions right here, what kind of reaction do those conditions remind you of? Well, this might remind us of alcohol dehydration. Okay? And if we think about alcohol dehydration, the first thing we did was to protonate the OH group to make it into a better leaving group. Okay? So that seems like a reasonable place to begin. This structure, H3PO4, this is going to be our acid. It's going to be hard to write a mechanism using phosphoric acid as drawn here because we can't really see where the available protons on phosphoric acid are. Okay? So pause the video and draw the Lewis structure of phosphoric acid, and then if you want, go ahead and start your mechanism. Well, here is the Lewis structure of phosphoric acid. I'll just put it over here. Make sure you draw out at least one of the OH bonds, because you're going to need to do that in order to be able to push the arrows in a convincing way. So there's the first step, okay? And then we're going to go over here. All right, so let's come up here. There we go. So what is our next compound in the mechanism? Well, we have this 6-membered ring here. We have a 5-membered ring there. And now we have protonated our OH group. Let's remember there's a hydrogen at that carbon. And then let's keep the numbers on here because that's really going to allow us to remain oriented in terms of where we are and where we're trying to go, and we'll be less likely to lose a bond or lose an atom if we have everything numbered correctly. All right, in the alcohol dehydration mechanism, the next thing was for the leaving group to leave. We now have a good leaving group here. Here's our molecule of, or at least incipient molecule of water. So now a molecule of water is going to depart, and we're going to get a carbocation. There we are. Again, let's number the carbons. There we go. Okay? So let's check our list, our to-do list. We have lost a molecule of water, so that looks good. We have broken the bond between C1 and the oxygen, so that looks pretty good. We seem to be on the right track. So now we've made a carbocation. We should always check and see whether this is an acceptable carbocation. What kind of carbocation is this? Is this a methyl cation? Is it a primary carbocation, a secondary carbocation, or is it a tertiary carbocation? This carbon, where the positive charge is attached to one other carbon and then a second other carbon. So this is a secondary carbocation. That's an acceptable carbocation. Not as good as a tertiary carbocation, of course, but at least okay. Now, what are the three things that carbocations can do? And which of those three carbocation fates do you think is most appropriate for this problem? Remember, we're trying to get to this structure right here. The three carbocation fates are add a nucleophile, lose a proton from next door to make an alkene, and the third one that we now know about is rearrangement. So of those three, given that the structure of this looks quite different from the structure over here, here we have a 6-membered ring and a spiral fused 5-membered ring. Over here we just have two 6-membered rings that are fused together in this different sort of way. So I would choose rearrangement. Okay? All right, so in terms of rearrangement, let's look at what we need to do. We need to break a bond between C10 and C6, and we need to make a bond between C10 and C1. And this we can accomplish through a carbocation rearrangement. If we take carbon 10, so let me just draw in carbon 10, here it is. It has two hydrogens attached to it. And what's going to happen here is that carbon 10 is going to detach itself from carbon 6, and we're going to move this bond over and make a bond to carbon 1. Okay? So let me read this arrow for you, because sometimes rearrangements can be a little bit difficult to see at the beginning. What this arrow says is take the electrons that were bonding between C10 and C6, remove them, take them away from where C6 is, and use them instead to make a bond between C10 and C1. All right? When you draw the product of a rearrangement step in a mechanism, here is a useful way to proceed, at least until you feel more comfortable with what's going on. Okay? So here's what I'm going to do. I'm just going to recopy exactly the previous structure, put the numbers on here, and then I'm going to take, hold on, this eraser, and I'm going to use this eraser, and I'm going to use this chalk. Let me put the CH2 here at where carbon 10 is. I'm going to take this eraser, and I'm going to take this chalk, and I'm going to do what this arrow said to do. That arrow said disconnect carbon 10 from carbon 6. So there we go. Carbon 10 is no longer attached to carbon 6. Use those two electrons to make a new bond. Oops. Use those electrons to make a new bond to carbon 1. Okay? So if I just come back over here really quick, I've broken the bond between carbon 10 and carbon 6, and I've made a bond between carbon 10 and carbon 1. This is a carbocation rearrangement. Specifically, it's the migration of an alkyl group. So this type of carbocation rearrangement, you may remember, is sometimes referred to as a Wagner-Meerwein type of rearrangement. Now you'll notice this ring is not very satisfactorily rendered in terms of its actual shape. It's sort of a distorted shape. But now that you've accounted for all the bonding changes, you can redraw this in a more standard way. And this is where numbering things really comes into account. Here's carbon 1 and etc. Carbon 2, 3, 4, 5, 6, and so on. And then let me just go back to this structure here, because I guess I didn't quite finish this off. Not only do I have to erase the bond that was broken and draw in the bond that was made, I also need to be sure I handle the charge accordingly. So once this has happened, this rearrangement has occurred, I don't have the positive charge on carbon 1. Where is the positive charge now? So I can erase it from here. Where is the positive charge? Well, the positive charge is at the carbon where the electrons were taken away from. And so if I put this up here, I've got the positive charge on carbon 6. Okay? So my rearrangement began with this secondary carbocation. We did this Wagner-Meerwein shift. We got this carbocation, which I just redrew in a more realistic shape. What kind of carbocation is this? Is it a methyl cation? Is it a primary cation? Is it a secondary cation? Or is it a tertiary carbocation? Well, the carbon with the positive charge is attached to 1, 2, 3 other carbons. So this is a tertiary carbocation. Carbocation rearrangements often, typically even, occur preferentially from a less stable carbocation to a more stable carbocation. And that's the case here. We rearrange from a secondary carbocation to a tertiary carbocation. The other thing I should perhaps include in my structure is that there's a hydrogen at carbon 1. Okay? So again, let's go back to the to-do list. I've whittled it down to just 2 things. I need to make a pi bond between carbon 1 and carbon 6, and I need to lose a hydrogen or break the bond between C1 and H. So back to our list of carbocation fates. Of the 3 carbocation fates, addition of a nucleophile is one of them. Loss of a hydrogen from next door to make an alkene is the second, and rearrangement is the third. Which of those 3 is the best one to pick to finish off our mechanism? It's elimination. I need to lose this proton and put a double bond into this place right here. The best base that I have in the reaction mixture for removal of that hydrogen is the conjugate base of phosphoric acid, which I generated in the first step of my mechanism. And so now I can just finish off this mechanism by removing this proton, making the double bond. That takes me to the final product. There it is. And then the other thing that has been regenerated is phosphoric acid, H3PO4. This removes the proton. So you'll notice this process is catalytic in phosphoric acid. We needed the proton at the beginning to make OH into a good leaving group. And then at the end, we needed the conjugate base of phosphoric acid to act as an acid to finish off the mechanism and to regenerate the catalyst. Okay? So this is an alcohol dehydration reaction, but the initially formed carbocation has the opportunity to rearrange before the elimination step. Okay? It wouldn't really be reasonable to expect you to predict this outcome. So if we come back over here, this would really not be, in my opinion, a reasonable problem if I just omitted the product and asked you to somehow predict this. Maybe you could. I mean, it's not completely impossible, but this is not that type of problem. It's not a give the products problem. It's give the mechanism problem. And in a give the mechanism problem, just to recap, you're given everything, the starting materials, the reagents, any reaction conditions, the product, and your job is to provide a reasonable step-by-step process for how that could happen.